me give you one example. This is ground, concrete, okay, or dirt. And when the dirt is wet, it can be conductive slightly. Okay. But when your operation, your wave frequency, you have a 1 kilohertz wave seeing this dirt. Dirt is behaving like a conductor for a very low frequency wave. But the same dirt, when it sees a high frequency wave, it behaves like a dielectric. So what does that mean? Now think back. Do you still listen to radios? You're using iPhones. Okay, you're so advanced. When I grew up, we don't have television, really. We only have black and white television. So basically, we listen to radio all the time. Okay. We have one radio station on campus. And do you happen to know how many stations are our radio frequency channel has? And just one for the entire campus. Why? Usually, entirely in Taiwan, we might have 100 radio stations, but each station only construct one single source antenna. Try to relate that fact to here. Because the radio frequencies are very low, right? Megahertz, hundreds of kilohertz. So that means even though they only have one station, you only have one station, right? You only have one station broadcasts. But then the ground, when the wave sees the ground, because it is working at a very low frequency, ground is behaving like conductors, like metals. What do metals do? Metals reflect waves, right? So low frequency waves can be reflected effectively by ground or by other buildings. So you only have to construct one station broadcasting these signals, but you're using the ground to act like mirrors. Okay? But what about our 3G, 4G, and eventually 5G signals? Do you know the frequencies of this 3G, 4G, 5G channels? Gigahertz, right? This is kilohertz or megahertz, but this, the ones we're using wireless Wi-Fi, gigahertz, extremely high. So the same dirt, ground, sees the high frequency component, it treats them like dielectrics. What do dielectrics do? They penetrate. Right? Therefore, on campus, we have dozens of cell phone stations. So now you know the reason why, because you cannot rely on the ground to reflect high frequency signals. You need to build a lot of these cells, and that's why you call it cell phone, right? Each cell, each station can only cover maybe 1 kilometers or 2 kilometers. But when your operational frequency is reduced, then your working coverage is extended. Okay? So due to this reason. Okay. So I'm trying to link purely theoretical results to real applications. Okay? Eventually one day you will become an engineer. You need to know that frequency dependence is extremely crucial, especially to electrical engineers. Okay. Same material, different operational frequency, the material behaves in a dramatically different way. Okay, so that's metal. I taught you about metal, so this is gold. This is the real part of epsilon for gold. I mentioned this to you. For typical metals, epsilon can be huge in terms of quantity, but they are negative. So now I'm showing you the proof. Epsilon, the real part of gold, is negative and very, very negative. Okay. So this is showing you again, when your operational frequency is, this is wavelength, okay? So wavelength here is high frequency and low frequency. So basically, whenever we think of metals, epsilon, the real part of the epsilon are usually negative. Okay. So they are very good reflectors. Okay. As you increase your frequency, the epsilon is becoming 0 and then it's positive, meaning metal can behave like dielectrics when your operational frequency is very, very high. Okay? So this is another confirmation to these two statements. Right? Low frequency, you have a conductor-like behavior. Extremely high frequency, you have a dielectric. Alright, so the magical thing is Maxwell's equations, the 4 equations, are extremely simple. And they are based on experimental observations. But up to now, those 4 equations can cover an extremely wide operational frequency range, all the way from the low frequency, radio frequencies, to the gamma rays. Okay? It's really magical. Experiments performed more than 100 years ago were able to predict the wave behaviors over such a wide frequency range. Right? 10 to the third, 1 kilohertz, all the way to 10 to the 12th, 10 to the 20th hertz. So it's really magical. So try to appreciate the contributions of Faraday, Gauss, and Maxwell. Great. Okay. So we have pretty much described how a given wave propagates in simple materials. Okay. So if you have a wave, then it propagates in this material with the E field and H field in the same direction, in the same speed. Okay? But basically the wave equation, both in the time domain or the frequency domain, these two sets of equations do not tell you where the wave is coming from. So we're eating chickens every day, but we never ask how the chicken's coming. It's derived from eggs, but okay, it's coming from the question: eggs comes first or chicken comes first? So I want to talk about the birth of a wave. It's really not covered in the textbook, but I think it's very important for you to understand how to create or give birth to a wave. So it's the same wave equation, but it's now inhomogeneous. What does inhomogeneous equation mean? In the wave equation, up to now, these two sets are both homogeneous in the sense you have no source, right? The right-hand side of the equality sign are both 0. Meaning, these waves appear as magical. They're there, and you cannot have the information where they come from. Okay, so now we're going to look into the details, how to create a wave. I know a lot of you are feeling sleepy now, so I'm trying to wake you up. Well, we talked about materials, and we talked about polarization vectors. We focus on the electrical dipoles. So a given material can give rise to induced electric dipoles when you have externally applied E field, right? So you just imagine you have one material. So these are different space, right? This material has lots of atoms or molecules for different location. So just imagine you have an inhomogeneous medium. So location 1, once you excite the entire medium with certain field, but this location is giving rise to this induced electric dipole. Okay? So these 3 electric dipoles are induced at different locations, but this one is having some moderate frequency, and this is the slowest frequency. This one is at the highest frequency. And they have different amplitudes, right? So let me just go through all the materials. So on the left-hand side, this material is very inhomogeneous, right? Very inhomogeneous. How do you mathematically describe this material? Can you use a simple epsilon? Of course not. So this is not a simple E. But over to the right, take a guess. So these two materials are excited by the same field, but somehow this one is very, very well behaved. So if you are a teacher or a professor, which class, just imagine all these atoms are the students. Which type of class do you like to teach? If you ever become a parent, and these are your children, which type of children do you like to teach? Take a guess. Choosing the right one, raise your hand. Good. Choosing the left-hand side, raise your hand. None. Oh, 102. As a university professor, I like to teach a class with students with extremely high variation in responses. Why? We're not in the military, right? If all the students respond in the same way, there's no reason for me to teach, right? So try to understand that. I'm always using this as a joke. As a parent, I do like to have this type of children, but whenever I think of their future, I want them to be independent. I want them to be able to express themselves. That's the type. Right? But here, again, I'm showing you a live demonstration of simple medium and not so simple medium. Right? But it's fine. I mean, mathematically, we can easily treat this polarized medium. Now, if you still remember, this is drawing out P vector for you, right? We assume if we have a homogeneous medium, every location is responding to my external field in the same way. So that polarized medium, I can easily capture the fact by this polarization vector as a function of space and time, but a simple medium. It's homogeneous throughout the locations. Okay? So D equals to epsilon 0 E plus P. we are only reviewing what we covered for electric materials, for dielectrics. Now you think about wave equation. The derivation of wave equation is nothing more than the combination of Faraday's effect and Ampere's effect. So now we have this curl B, right? Curl of mu times h is B. But B is, if you still remember, B is related to D. So that means intrinsically, Maxwell already contained the possibility to create the wave. So curl of B, D is epsilon 0 E plus P, right? So you actually have two terms. This is saying that if you don't write epsilon E, you don't write D is equal to epsilon E, right? Or it is equal to epsilon 0 E plus P. You have two ways to express D. So now that if you really want to know how the waves are generated, you separate the effects out. You need to look into the induced dipoles independently. That's all you need. Previously, we combined these two as epsilon E. So you cannot really tell the difference of the free externally applied field from the induced dipoles. But now that we explicitly separate the two terms out, and now we can insert that back into the wave equation, right? So the same derivation, the same assumptions, is only we're really looking into how the induced dipoles are working. What are their functionalities? Then, on the left-hand side, you have the E field intensity. On the right-hand side, so this is basically the wave equation in type domain. But now we isolate the effects of the induced electric dipoles out. So now on the right-hand side of the equality sign, it's not zero anymore. So try to compare this one to the one we derived on last Wednesday. We're always solving for the E field or H field, but in the past, on the right-hand side, we have nothing, right? On the right-hand side, we have zero, meaning that we cannot create waves because we don't have a driving source. But now that on the right-hand side, it's non-zero. So we have a driving source. Up to now, are you able to come up with a simple statement to teach yourselves how can you create a wave? If you have time varying dipoles, you might be able to create waves, right? Can you be more detailed, more specific? What type of motion do these charged particles have to have? Do you still remember this P? P is like, well, P is Q D as a function of time, right? Distance, the separation of the charges. So So now you have time-varying electric dipoles, meaning that the separation between the two positive and negative charges is a function of time. So if you replace that, you might have a lot of dipoles. So you replace into that. Now can you tell yourselves how to create a wave? Your charged particle needs to be, of course, time dependent in their location, and it has to have what type of motion? X or D is space, right? Space making one temporal derivative is called velocity. Velocity making another temporal derivative is called acceleration. Thank you. So in the final examination, if I only give you one problem, I want you to generate a wave in front of me. Do you know how to do it? Yeah. You take a charge and you do something with acceleration, right? And then you can enjoy the creation of a wave. So this charged particle needs to experience acceleration. Once you have an accelerating charge, you can have a wave. Okay? So basically, you can accelerate a charge in pretty much three ways. One is linear acceleration. Take a close look. It only appears for a second. What? Linear acceleration. Or you can have this cyclotronic motion. This is exactly how synchrotrons are generated. Do you know synchrotron center is just behind us? 同步辐射. Synchrotrons, you accelerate or you make the charged particle at extremely high speed, and when it turns, right? When it turns the direction, it's suffering acceleration, so radiations come out. Just drop it. So if you have the ring, usually synchrotrons have ring-like. So in this location, the charges are extremely accelerated with high speed. When it's reaching very high speed, it bends. When it bends, it suffers from very high acceleration, right? Because velocity is the vector. So this is v, and this is v. You need to have great force to bend this charged particle streams. So usually this is where you have radiations. Okay. So if you go to any synchrotron center, they usually have this ring, and all the laboratories are stationed here, because this is where you have the highest velocity and radiating the highest energies. Okay. This is exactly the working principle of synchrotrons. And we are just adjacent to National Synchrotron Center. And you should think about it, and you should visit the National Synchrotron Center, and maybe you can work in it, because now you understand the working principle. Okay. The third time, you bump, right? When you play pool, you're creating waves every day. Okay. So a lot of high school students who do not like to study, they go out and play pool. They are wave makers. You should respect them. Okay. All right. Last slide for this class. I want to leave it here. So take a good look for 10 minutes. We are going to take a 10 minutes recess. After 10 minutes. We'll come back and you tell me what you have observed. This is a simulation for generating waves. Okay? So you have to ask yourselves, where are the accelerated charges? And where are the generated waves? What are their special characteristics? Okay, so take a good look for 10 minutes.